Chapter 21. The Role of Information Technology in Sterile Processing. Introduction. Welcome to the comprehensive study of Chapter 21, which focuses on the role of information technology in sterile processing. In this session, we explore how information technology, commonly referred to as IT, has fundamentally revolutionized the sterile processing department, also known as the SPD. This transformation represents a significant shift from manual, vulnerable systems to automated, data-driven precision. Historically, sterile processing departments relied heavily on handwritten logs and human memory to track thousands of instruments. Technicians were required to remember the physical location of trays or manually record sterilization loads in paper logbooks. This method was fraught with the potential for human error. Today, sophisticated computer systems manage inventory, track sterilization loads, and locate specific instruments in real time. The primary goal of implementing these systems is to replace manual, error-prone processes with automated, data-driven systems that enhance both patient safety and operational efficiency. While efficiency and cost reduction are significant benefits, the core drive for these systems is patient safety. This ensures the department knows exactly what instruments were used on which patient and confirms that they were processed correctly. Role of computer-based information systems. Computer systems in the sterile processing department serve three primary functions that are critical to modern operations: data management, standardization, and connectivity. First, data management allows computers to store vast amounts of historical data. For instance, sterilization records from years past can be archived and retrieved instantly. This capability is physically impossible to manage efficiently using only paper storage. Rapid data retrieval is critical for audits, legal verification, and infection control tracking. Second is standardization. IT systems enforce consistency across the department. For example, a digital count sheet ensures that every technician packs a tray exactly the same way every time, reducing variability. Whether the task is performed by a technician on the morning shift or the night shift, the system dictates the process, ensuring the surgeon receives the exact same set configuration for every procedure. The third function is connectivity. Sterile processing systems do not operate in a vacuum. They interface, or communicate, with other hospital systems, most notably the operating room, or scheduling system. This connectivity allows the department to view upcoming surgical schedules and automatically generates a pick list of required case carts. This predictive capability informs the staff of what is needed before the patient even arrives in the holding area. Overview of information technology in the healthcare setting. To fully understand where the sterile processing system fits within the larger facility, it is necessary to distinguish between the different systems used in a hospital setting. First, there are ADT systems. ADT stands for admission, discharge, and transfer. This system tracks patient movement through the hospital. It registers patients upon arrival, tracks their room assignment, and records their departure. Because this system handles sensitive patient identity information, strictly following HIPAA regulations regarding data privacy is a critical responsibility here. This data is vital for linking specific patients to the instruments used on them. Second, there are materials management systems. These are used primarily to manage the ordering and inventory of consumable supplies. This includes items such as disposable gloves, sterilization wraps, and detergents. These systems track bulk items that are used once and discarded. Finally, we have instrument tracking systems. This is the specific software used by the sterile processing department to manage reusable assets. Unlike materials management systems, which track disposable boxes, instrument tracking systems manage expensive surgical assets that cycle through the decontamination, assembly, and sterilization process hundreds or thousands of times. This tracking system answers three critical questions for the department. The first question is, what do we have? This refers to inventory. The second question is, where is it? This refers to location. The third question is it safe? This covers process history and sterilization status. Tracking systems for the SPD. Having established the broad types of hospital systems, we now turn our attention to the specific tracking methods used within the sterile processing department. This section is heavily emphasized because a technician must be able to distinguish between the specific technologies used to identify and track instruments. Essentially, the department needs a reliable way to read the identity of instruments and trays. The industry currently relies on three main technologies to accomplish this: linear barcodes, matrix barcodes, and radio frequency identification, also known as RFID. First, let us examine linear barcodes, often referred to as one-dimensional or 1D barcodes. These utilize the traditional picket fence style of vertical lines, similar to the barcodes found on consumer products. While they are common, they have significant limitations in the sterile processing environment. A linear barcode contains a limited amount of data and requires a flat surface and significant space to be legible. Because of this size requirement, linear barcodes are usually applied only to the outside of sterilization trays or peel pouches. They simply cannot be placed on small, individual instruments like a hemostat or a pair of iris scissors because there is insufficient room on the handle for a linear code. This limitation leads us to the second technology, the matrix or two-dimensional, 2D, barcode. This is often referred to as a data matrix. Visually, this looks like a square consisting of a grid of dots or squares, rather than lines. This is the preferred method for tracking individual surgical instruments for several critical reasons. First, a data matrix can store a large amount of data in a very small space. Second, it has built-in redundancy, which means it remains readable even if it is slightly damaged or scratched. But the most significant advantage is that these codes can be laser-etched directly onto the metal surface of the instrument. This etching is durable enough to survive thousands of sterilization cycles, including high-temperature steam and harsh chemical washes. Because they are tiny and durable, data matrix codes allow for item-level tracking. This technology is the global standard for complying with the FDA's Unique Device Identification, or UDI, system, allowing us to track the history of a specific scissor rather than just the whole tray it sits in. The third technology is radio frequency identification, or RFID. By definition, RFID is a system that uses radio waves to wirelessly transmit the identity of an object via a tag to a reader. The critical advantage of RFID compared to barcodes is that it does not require line-of-sight scanning. With a barcode, the scanner must physically see the code. If the code is covered by a sticker, smeared with dirt, or turned away from the scanner, it will not work. With RFID, a technician can track an item just by walking past it or having the item pass a sensor mounted in the ceiling. This allows for the scanning of a case cart full of trays without ever opening the cart doors. Tracking systems meet specific needs. Within the realm of RFID technology, we also utilize what is called a real-time location system, or RTLS. In an RTLS setup, the tags actively ping their location to the network. This allows the system to show exactly where an item is on a digital map of the hospital. RTLS is specifically designed to meet the need for tracking mobile assets that move frequently through hospital corridors, such as 4 pumps, crash carts, or case carts. It is vital to understand how these technologies enable different levels of tracking specificity. You must distinguish between set-level tracking and item-level tracking. Set-level tracking tracks the basket or container as a whole unit. It can tell you that a specific major basic set is currently inside a sterilizer. However, it cannot tell you if a specific scissor inside that tray was swapped out, nor can it tell you how many times that specific scissor has been used. It treats the contents of the tray as a single anonymous block. Item-level tracking, on the other hand, tracks every single instrument individually. This utilizes the 2D data matrix code etched on every tool. The advantage here is precise history. It enables the department to track specific maintenance history, such as alerting staff that a specific scissor has been used 50 times and is due for sharpening. It is also essential for pre-on protocols, as it allows the facility to link a specific instrument to a specific patient, ensuring accurate tracing in the event of an infection control issue. Features of instrument and equipment tracking systems. Moving deeper into the functionality of these technologies, we must examine the specific features that distinguish different tiers of tracking software. Tracking systems are generally categorized into two tiers: basic systems and advanced systems. It is important for a technician to understand the capabilities and limitations of each. Basic systems provide the fundamental administrative tools needed to run the daily operations of the department. Their primary functions include generating count sheets, which act as the recipes for assembling trays, and printing labels for sterilization packs. Beyond these administrative tasks, basic systems track the last known location of an item. For example, if a staff member searches for a missing tray, a basic system might indicate that it was scanned in decontamination at 10 o'clock in the morning. However, it typically will not offer much more detail beyond that single timestamp and location. Advanced systems, however, offer robust tools for management and quality assurance that go far beyond simple location tracking. We will examine 4 key features of advanced systems. First is productivity reporting. These systems track exactly how many trays a technician assembles per hour. This data is used by management to measure individual performance and assess the overall output of the department. The second feature is quality assurance. This is a critical safety mechanism. Advanced systems can actually block a technician from printing a sterilization label if they have not documented essential safety checks, such as the biological indicator result. If the safety step is skipped or not recorded, the system halts the process, preventing a potential safety violation from moving forward. The third feature consists of maintenance logs. In this capacity, the system acts as a preventative maintenance scheduler. It can alert staff when a tray needs sharpening based on actual usage data rather than a guess. For example, the screen might display a warning stating that a specific tray has been used 50 times and must be sent for repair. This prevents dull or malfunctioning instruments from reaching the operating room. The fourth feature is staff competency. This feature directly supports education and compliance. The system can require a technician to view a photo or a video of a complex instrument assembly on the screen before they are allowed to proceed with packing that tray. This ensures that even if a technician has not seen a specific device in months, they have immediate access to the correct instructions, reducing the likelihood of assembly errors. Tracking loaned instrumentation. Beyond managing the facility's own assets, the department faces the major logistical challenge of tracking loaned instrumentation. These are trays brought in by vendors for specific surgeries, often orthopedics or neurosurgery, which arrive and leave on a rotating basis. Advanced IT systems help manage this complex flow in 2 distinct ways. First, systems utilize vendor integration. Advanced tracking software allows vendors to access a secure online portal where they can input their loaner inventory lists before they even arrive at the hospital. This proactive step means the sterile processing department knows exactly what is coming and can prepare for the workload. Second, the system enforces a rigorous check-in and check-out process. The software forces a documented inventory check when the loaner arrives and again before it leaves the facility. This provides a digital paper trail that prevents disputes regarding lost instruments. For example, it ensures that the hospital is not billed for a screw caddy that the vendor actually left behind at another facility, as the system serves as the definitive record of what entered and exited the building. Tracking and planning for SPD technicians. The final major function of these systems is to assist in the operational management of the workforce. Beyond just locating items, IT systems collect data that helps managers run the department more efficiently. We focus here on 2 critical concepts: turnaround time and priority lists. Turnaround time, commonly abbreviated as TAT, is a standard metric in the sterile processing industry. It is precisely defined as the time interval from the moment an instrument set is dropped off in the decontamination area until it is sterilized, cooled, and ready on the storage shelf. By analyzing TAT reports, managers can identify workflow bottlenecks. For example, if the data shows that turnaround time slows down significantly every day at 2 o'clock in the afternoon, the manager knows to schedule more staff during that specific shift to handle the influx of work. Finally, we have priority lists. Because the tracking system interfaces with the operating room scheduling system, it knows which cases are coming up next. Computer screens located in the decontamination area can display a live priority list. This tells technicians exactly which cart to wash first. For instance, the screen might display a message stating that a specific hip set is needed in 2 hours. This ensures that urgent items are processed immediately rather than sitting at the bottom of a lift while less urgent items are washed, thereby directly supporting the surgical schedule. Conclusion. As we wrap up the technical breakdown of these systems, it is helpful to conceptualize the role of information technology using a biological analogy. Think of the IT system as the nervous system of the sterile processing department. Just as the human nervous system provides the memory and logic that coordinates the body's movements, the IT system provides the essential memory and logic needed to manage the thousands of moving parts in a modern facility. It coordinates the complex flow of contaminated items returning to decontamination, clean items being assembled in the clean room, and sterile items being safely stored or distributed to the operating room. However, there is a critical limitation to this technology that you must understand, often summarized by the industry phrase garbage in, garbage out. This concept reminds us that technology is not magic, it depends entirely on the accuracy of the human input. The system is only as reliable as the technician using it. Consider this practical example. If a technician scans a sterilized tray to shelf A in the computer system but physically places it on shelf B, the system is now useless for finding that tray. When a surgeon urgently needs that instrument, the computer will direct staff to shelf A, but the item will not be there. In that moment, despite having $1 million tracking system, the item is effectively lost until someone physically hunts it down. Therefore, discipline in scanning and data entry is just as important as the technology itself. Without human accuracy, the system fails. Key terms review. To reinforce your understanding of Chapter 21, we will now conduct a focused review of the key terms. These are the specific definitions you need to memorize for the certification exam. First is radio frequency identification, commonly known as RFID. This is defined as a system that uses radio signals to locate and identify tagged items without requiring line-of-sight scanning. The key phrase to remember here is, without line of sight. Second is the matrix barcode, also known as the 2D barcode. This is a barcode consisting of a grid of dots or squares rather than vertical lines. Its defining characteristics are that it allows for high data density in a small space and can be laser etched directly onto metal instruments. This durability is what makes it the standard for tracking individual surgical tools and adhering to UDI standards. Third is Real-Time Location System, or RTLS. This is the specific technology used to track the immediate physical location of assets, such as 4 pumps or case carts, as they move through the facility. It provides a live map of where equipment is located at any given moment. Fourth is turnaround time, or TAT. This is the time interval between the start and end of a process. Specifically for the sterile processing department, it is measured from the moment an item is dropped off in the decontamination area to the moment it is placed on the sterile storage shelf. Memorize these start and end points, as they define the efficiency of the entire department. Core Exam Concepts Part 1. We will end this chapter with a review of the core exam concepts. These are the specific points where students often lose points on the exam, so pay close attention to the distinctions made here. Concept 1 concerns the primary goal of IT systems. Here is the exam trap you must avoid. You may see a question that asks for the primary purpose of implementing a tracking system. You might be tempted to answer efficiency or cost reduction. While those are significant operational benefits, the standard exam answer is usually patient safety and standardization. The reasoning is that tracking systems allow for the rapid location of instruments used on specific patients during a recall or infection outbreak. That is the safety component. They also enforce a consistent packing list for every technician, ensuring the same quality every time. That is the standardization component. Concept 2 involves the technology comparison between barcodes and RFID. This is a frequent exam topic. Remember the limitation of barcodes, they require line of sight. The scanner must physically see the barcode. If it is covered, dirty, or damaged, it will not scan. Also, remember the distinction between 1D and 2D barcodes. 1D linear barcodes are used for trays and have limited data capacity. 2D matrix barcodes are used for individual instruments, have high data capacity, and can be laser etched directly onto metal. Contrast this with RFID. Its main advantage is that it does not require line of sight. Readers can detect tags automatically as they pass sensors, making it ideal for tracking mobile equipment without human intervention. Core Exam Concepts Part 2. Continuing with our review of essential exam topics, we move to Concept 3, System Interfacing. The core concept here is that the sterile processing tracking system does not work in isolation, it talks to other hospital systems. The key interface you need to know for the exam is the connection to the operating room scheduling system. The specific function of this interface is to read the surgery schedule and automatically generate a pick list or case cart list. This automation tells the sterile processing staff exactly what trays are needed for upcoming cases, removing the need for manual guessing or phone calls. Concept 4 deals with data integrity and downtime. We return to the fundamental rule of garbage in, garbage out. A computer system is only as accurate as the human input. If a technician scans a cart to storage but leaves it in decontamination, the system data is wrong, and the cart is effectively lost. Additionally, you must be aware of downtime protocols. Facilities must have a manual backup policy, usually involving paper logs, ready for immediate use when the computer system goes down. Operations cannot stop just because the internet is out or the server fails. You must know how to manually document sterilization loads to ensure surgeries can continue safely without the aid of the computer. Concept 5 concerns computer security. You must always remember to log off your computer terminal when leaving a workstation. Because these systems contain sensitive patient data protected by HIPAA, leaving a terminal logged in allows for potential unauthorized access. The exam will expect you to know that data security is a personal responsibility of the technician. This concludes our comprehensive study of Chapter 21, the role of information technology in sterile processing.